Welcome along to the next video in this series called Exploring the Solar System. My name is Dr. Alan Wood and I'm a senior lecturer in the physics team at Nottingham Trent University. So I'll just hit screen share and bring up the PowerPoint we're going to have a little look at today. This session is called The Lights in the Sky. So in the last session, we said that the night sky has fascinated people since the dawn of time. And there's some lovely descriptions of the night sky, such as calling the Milky Way the backbone of night. Because if you go somewhere really dark, you've got this arc spanning the sky, and it looks like it's holding up the whole of the night sky. We moved on to talk about some of the very early ideas about making measurements of the natural world, about early experimentation. And we said that at the Great Library in Alexandria, the size of the world was established. How was it established? Well, a report reached the Great Library saying on the 21st of June at noon, sticks at a place called Syene cast no shadow. But they did as Alexandria. And the distance between Alexandria and Syene was measured. The angle that the sticks cast when they created this shadow at Alexandria was measured, and from this, the size of the world could be established. How? Well, sorry, let's just have a look. So here is a little diagram of the Earth. And here are the two sticks. We've got a stick here at Syene, and we've got a stick here at Alexandria. And here are the sun's rays coming in. Because the sun is so far away, we can assume that these rays are parallel. And so this distance here is 800 kilometers. This angle here is 7 degrees. Now by Z angles, this angle over here will also be 7 degrees. And so, from these data, the size of the world can be established. Now, what we can see is 7 degrees corresponds to 800 kilometers. Therefore, 1 degree corresponds to 114 kilometers. If we do the number of kilometers divided by the number of degrees, we find out how many degrees 1 kilometer corresponds to. Now, we know that a circle contains 360 degrees. So we can find the circumference of this circle, 114 kilometers multiplied by 360 degrees gives us 41,000 kilometers. We know the circumference of a circle is given by 2 pi r, where r is the radius. Therefore, we can say the radius is the circumference over 2 pi. We can say that the circumference is approximately 41,000 kilometers. So 41,000 kilometers over 2 pi gives us 6,500 kilometers. And the currently accepted value for the radius of the Earth is 6,378 kilometers. So think about that with sticks and shadows. The size of a world can be determined. And this also shows how much we can do, what wonderful physics we can do, if we think about the problem as carefully as possible. And that often we don't need the most sophisticated equipment if we use the most brilliant device of all, which is our minds. So what else happened at the Great Library in Alexandria? Well, the short answer is tons of stuff. We talked about some of the research halls in the last session. We talked about how they had an observatory, how they had a zoo, all these wonderful, wonderful things. But let's just look at a few other results. Hipparchus mapped the constellations. Together with Ptolemy, they first classified the stars in brightness and apparent magnitudes. What else would a classification like this would have seen? Well, it would have seen some of the objects in the sky, some of the lights in the sky appeared to move. And these are the planets, the wandering stars. The brightest stars were classified as being magnitude 1. The dimmest visible with the eye as magnitude 6. So it's a scale here of 1, 2, 3, 4, 5, 6, where 6 was the dimmest star. And we still use this magnitude scale today. Now, what we now want to think about is a model to explain the universe. And the basic patterns have been observed in the night sky for thousands of years. What were these? Well, the sun rises in the east, ascends in the sky, and sets in the west. There's a yearly pattern to the maximum elevation of the sun. So the sun will be a certain amount above the horizon in winter and a certain amount above the horizon in summer. There's a pattern there. The stars are in apparently fixed patterns, rotating around an apparently fixed point. We see the same constellations coming back again and again and again. But there's an annual pattern to the orientation of the constellations at midnight. So what does that mean? Well, it means like Orion might be visible from the UK in the autumn sky, but not at a certain time of the evening, but not at that same time of the evening in spring. By the time it gets around to autumn, Orion is then visible again at the same time in the evening as the previous autumn. There's this pattern. And these patterns need to be explained. Astronomy is fundamentally an observational science. We observe the natural world, but we need a model to explain it. So astronomy is an observational science supported by modeling. Ptolemy came up with a model of the universe, an Earth-centered model. He came up with this in the 2nd century. So he thought that the Earth was at the center of the universe and everything else was going round the Earth or supported in some way. It included the following ideas. The idea was the Earth is stationary. Things fall to Earth unless supported. So you could observe this. So there's observations and experimentation, so, going into his ideas within here. He said that the heavens were perfect and unchanging, which was a curious idea, given that the planets for wandering stars had already been seen, comets had been seen, eclipses had been seen. So perhaps they weren't unchanging. But he said the heavens were perfect and unchanging, and the perfect 3D shape is a sphere. So he felt the whole thing should be based on spheres. Now, the planets show retrograde motion. The planets for wandering stars move one way and then the other. So let's just look at this for example. So here we've got a diagram showing the Earth, and we've got the distant, apparently fixed stars. Now, if we look at the motion of a planet across the night sky, it will appear to move like this compared to the fixed stars. We'll see it here, then 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 here. And when it is moving this way, we call it prograde. This way, retrograde. This way, prograde motion. And what Ptolemy imagined was he imagined these planets to go around the Earth on transparent spheres attached to these spheres by off-center wheels. And he had 7 spheres in his model, one for the Moon, one for Mercury, one for Venus, one for the Sun, one for Mars, one for Jupiter, and one for Saturn. And one of the big strengths of his model was observations and theory agreed. So he had things like this. So here's the Earth, and here is Mercury. So Mercury here is going around the Earth on this large sphere called a deferent. And then it's attached to this deferent by an epicycle. And it's going round and round and round this deferent on this epicycle. And the net result of this is to get motion like this, going prograde, retrograde, prograde, retrograde, prograde, retrograde, prograde, etc. And one of the big strengths of this model was that observations and theory agreed. And it held sway for well over a millennia until the Copernican revolution. And that's what we're going to talk about next time. Okay, so thank you very much for your attention. That's where we're going to end this particular session, and I look forward to speaking to you on Tuesday of next week.